Hello, welcome to my channel. This is an educational channel attempting to shed some light on some of the theories of everything that I've become aware of over my life, the ones that I think can benefit the general public in the most profound ways. And today is video number 313 on the reciprocal system of theory from Dewey B. Larson. And Mr. Larson lived in the United States in the 20th century. He first had his first epiphanies about the reciprocal system back around 1930. Kept his day job, but worked out some of the kinks at night, and it took him about 25 years for him to put out his two fundamental postulates that articulated the groundwork for the reciprocal system, and then another 30 years of writing books after that before he died in 1990, and left behind a dozen or so books and 50 or so articles, numerous other contributions. And the basic idea is that we live in a universe that is composed entirely of motion, not space, not mass, and not energy, but motion. And motion, according to his definition, is the relationship between space and time. Sets up a generalized reciprocal relationship between space and time. Motion is basically a fraction with space or time as the numerator and time or space as the denominator. And time and space both have their coordinate aspects, meaning that they come in 3 dimensions. They both have their clock aspects, meaning that they progress in a scalar manner, which is a motion that has a magnitude but no particular direction. Like a clock is always getting later and later and later, but in no specific direction. And spots on a balloon. If you blow up the balloon, the spots are all moving away from each other, but in no particular direction. This concept of scalar motion is what we're going to get into today. But I also wanted to say that both time and space are quantized, meaning that there is a minimum unit of space and a minimum unit of time. And if you don't have that full unit, then you don't have anything. If you don't have a full unit of space, you don't have any space. If you don't have a full unit of time, you don't have any time. And if you have 1 unit of space and 1 unit of time, you have the speed of light, which is what Larson calls unit speed. And that unit speed in Larson's system is the state of rest of the universe. So in a universe of motion, the state of rest is to be in motion at the speed of light. And there is an entire half of the universe where the speed is greater than the speed of light, which Larson refers to as the cosmic sector. This is all nonsense to an Einsteinian who believes that the speed of light is the maximum speed of the universe. And Larson gets into that in this explanation that we're going to get into right now. This is a paper that is just called Scalar Motion. He wrote this paper and delivered it in 1981. And it might take a few days for us to get through this one. But this is an important paper. If you can understand scalar motion, when Larson says the universe is made out of motion, he's particularly referring to scalar motion. Scalar motion is a concept that scientists know about, but they've never really emphasized its significance. And so Larson takes that concept of scalar motion and he really runs with it here. Okay, scalar motion. When a new physical theory appears, one of the first objectives of the supporters is that the theory is to find a crucial experiment, an experiment whose results agree with the new theory but are definitely in conflict with its predecessors, the other theories. This is a difficult undertaking, not only because it is hard to find an experiment of the right kind, but also because the results of that experiment, if an experiment is found, can usually be accommodated to existing theory by ad hoc assumptions of one kind or another. And the scientific community prefers to accept a modified theory of that kind in preference to an entirely new theory, even if the modifications require such wild ideas as black holes or charmed quarks. Nevertheless, a crucial experiment occasionally does make its appearance. Perhaps the most famous was the Michelson-Morley experiment from the late 1880s. And the constant speed of light disclosed by that experiment was devastating to the Newtonian system and created a conceptual vacuum that cleared the way for the acceptance of Einstein's relativity theories. My associates and I have naturally been on a lookout for a crucial experiment of this kind, and many leads have been followed up. Dr. Huck has an electrical experiment underway. Dr. Kramer has been working with a project that involves measuring the positions of the moon and many other ideas in various stages of development. Last year at Huntsville, and just as an aside, I know NASA has a facility there. I was under the impression that Larson did give a few talks to NASA in the 60s. This is, I guess, referring to 1980. But anyway, he says, last year at Huntsville, I gave a preliminary report on what will be my contribution to this project. So I don't know if that is a talk at NASA. I'm pretty sure that the people at NASA ignored everything that he said when he did talk there. But, and we might be grateful for that. Last year at Huntsville, I gave a preliminary report on what will be my contribution to this project. I was not able to devise a crucial experiment, but what occurred to me was that we could reach exactly the same point by identifying some previously unrecognized result of some earlier experiment. After all, we're not interested in the crucial experiment itself. What we want is the crucial piece of information that is derived from that experiment. And it actually makes no difference whether we get that from a new experiment or an old one. The public library in my home city is currently featuring a sign that says, "A book is always new if you have never read it." The same is true of physical facts. A physical fact is always new if it has never before been recognized. In the course of my investigations over the past 40 or 50 years, I have uncovered a great many hitherto unrecognized or disregarded physical facts, a surprisingly large number of them. But the one that fits our present requirements is a hitherto unrecognized property of scalar motion. Scalar motion itself is well known, although not by that name. For example, when the recession of the distant galaxies was first discovered some years ago, The astronomers needed an analogy to help explain the nature of that motion, and they knew right where to look for it. Almost every such explanation reads something like this one, which was taken from a current astronomical text. The common analogy likens the galaxies to spots on the surface of a balloon that is being inflated. As the rubber stretches, all the spots move away from each other. The widespread use of this analogy testifies to the general understanding that the motion of the spots on the expanding balloon and the motion of the distant galaxies is in some way different from ordinary motion. But the importance of that motion is not seen to be sufficient to justify any systematic exploration of its properties. After all, nobody is very much worried about the physics of expanding balloons. But that situation was changed very drastically by the development of the theory of the universe of motion, because scalar motion plays a very important part in that theoretical structure. So it was necessary for me to undertake the full-scale investigations of scalar motion that had not hitherto been attempted. If we examine the motion of the spots on an expanding balloon in isolation, without placing the balloon in a reference system or introducing a reference system into the balloon, or if we construct a similar mental picture of the recession of the distant galaxies, there is no way by which we can distinguish the motion of any one spot or any one galaxy from the motion of any other. Each spot and each galaxy is simply moving outward, away from all others at a constant rate of speed. That motion has only one property, a scalar magnitude. Such a motion is, by definition, scalar. The scalar motions readily accessible to observation are not isolated in the manner of those I have mentioned, but are connected to a physical reference system in some manner, as for instance by placing the balloon on the floor of a room. The physical coupling to the reference system provides the directions that the motions themselves do not have. If the coupling is fixed so that the directions are likewise fixed, then the combination of a scalar motion and a coupling to the reference system behaves in most respects in the same way as an ordinary vectorial motion, and it is not currently distinguished from a vectorial motion. Here is a place where a very important point has been overlooked. It is recognized that the balloon can be placed anywhere in the room, and it follows that the motion of any particular spot can take any direction in the reference system. But what has not been recognized, or has not been clearly recognized, is that the ability to take any direction is not limited to a constant direction. For example, the balloon may be rotated. The effect of a continuous rotation of the coupling to the reference system is to distribute the scalar motion over all directions in the dimension or dimensions of rotation, thus producing a distributed scalar motion. The properties of that distributed scalar motion are quite different from the properties of combined vectorial motions in different directions. In vectorial motion, the magnitude and the direction are interrelated. For example, if a vectorial motion of magnitude x in a specific direction is superimposed on a vectorial motion of equal magnitude in the opposite direction, the resultant is 0. Similarly, vectorial motions of equal magnitude in all directions add up to no motion at all. But the magnitude of a distributed scalar motion is not altered by the changes in direction. The balloon example is a relatively unimportant motion, originated and maintained by human action. But the fact that such motions exist means that the same kind of motions may originate from natural causes. So we thus arrive at the conclusion that there probably exists somewhere in the physical universe a class of distributed scalar motions that are not currently recognized as motions. As soon as we reach that conclusion, it is almost immediately apparent that the reason for the lack of recognition is the prevailing attitude toward the concept of force. Force is defined for scientific purposes as the product of mass and acceleration. Motion itself is measured on an individual mass unit basis as speed or velocity. That is, each individual mass unit moves at that rate. On a collective basis, it is measured as the product of mass and velocity, which is currently called momentum, but in earlier days was known by the more descriptive name of quantity of motion. The time rate of change of the motion is an acceleration on the individual mass unit basis, and the product of mass and acceleration, or force, on the collective basis. This obviously means that force is specifically defined as a property of motion. And it follows that force cannot be autonomous in the manner in which the so-called fundamental forces of nature are currently regarded. Every fundamental force is a property of a fundamental motion, but that creates problems for present-day science. For example, the electric charge produces an electrical force, and so far as we can tell, it produces that force directly with no sign of any intervening motion of the kind that is required by the definition of motion. Present-day science handles that problem very simply by ignoring it. But if we want to actually resolve the problem, what we need to do is to identify the electric charge as a distributed scalar motion. The charge itself is the motion, so we don't need that intervening motion that we don't find. This process of identification is a necessary part of all scientific work because the entities with which we deal don't come equipped with labels. The process itself is simple enough. It operates on what is sometimes called the duck principle. You are familiar with that, I presume. If it looks like a duck, and it swims like a duck, and it waddles like a duck, and it quacks like a duck, then it's a duck. We can illustrate the application of that principle by a simple example. Out in the depths of space, we see certain objects that we call stars and planets. It is not obvious from visual observation what those stars and planets are. At one time, it was thought that they were simply holes in the sky that let the light shine through. Since then, the properties of matter have been determined where we are in direct contact with it, and some of the properties of the stars and planets have also been determined. The two have been correlated, and whenever a comparison has been made, they have been found to be identical. That justifies us on this basis of the duck principle in concluding that the stars and the planets are aggregates of matter. In exactly the same way, we are identifying the electric charge as a distributed scalar motion. This is the same conclusion that I reached earlier in my theoretical works, But the situation is now entirely different. That theoretical conclusion had no meaning to anyone who was not willing to accept the premises on which it was based. And any scientist, or anybody else for that matter, had the option of accepting or rejecting it. That option is no longer open. We have now demonstrated that the identity of an electric charge as a distributed scalar motion is a necessary consequence of positively established facts, and the scientist has no option but to live with the facts. What I have said so far covers essentially the same ground that I covered in the preliminary talk last year at Huntsville, and it may be that I have been imposing on those of you who heard the previous talk by subjecting you to the same thing twice. But there are two reasons for so doing. In the first place, I wanted to emphasize the status of these findings with respect to distributed scalar motion as the equivalent of the result of a crucial experiment. The other reason is that it has been possible to extend those conclusions very materially during the intervening 12 months, and I wanted to talk to you a little about those extensions. My original intention, as I mentioned to some of those who were present at the conference at Huntsville, was to write an article for some appropriate scientific journal that would cover the scalar motion findings. And as soon as I got home from the conference, I started to work on that article. But coincidentally, I continued the investigations, and the results of those investigations accumulated so rapidly that it was very soon apparent that the idea of an article was impractical and that the amount of material I had could not be covered in anything less than a book-length presentation. So I proceeded with the preparation of the text of such a book, and in thinking over the subjects that might be of interest to you tonight, I decided that perhaps you might be interested in a sort of preview of the contents of that volume. Okay, I think we're going to stop it right there, and we will get into the second part of this paper tomorrow. So we're going to get into, I guess, a preview of the contents of that new volume. I'm not sure what book he's referring to. He did write a book in 1982 that's called The Neglected Facts of Science. So it may be that one. And frankly, that actually is one of Larson's books that I've not studied too thoroughly. So I'm learning this stuff as we go along, as well as you are. It's good to hear it multiple times. And these are difficult and unfamiliar concepts. So scalar motion is the name of this article. And that's what we're learning about. Who would have thunk it? Okay. Thanks for tuning in today, and have a great day.